So now that we know how to search a binary search tree, we're going to look at the ways that we mutate them, inserting and deleting. Insertion we'll go over in the lab for the course, so here we're just going to focus on deleting something. And the idea is pretty straightforward. If you need to delete a thing, you first off have to search for it, and then if you find it, it's going to be the root of some subtree. It's possible a subtree is really small, it could just be a leaf, or it could have subtrees of some amount of size. So if we want to delete something, we obviously don't really have much to do if the tree is empty. It's not going to be there. If the root is what we're looking for, then we're going to need to delete that. Otherwise, we're going to recursively go through left or right, trying to find where we need to delete something and then deleting it. And so once again, we're using that strategy of a helper method, delete root, which is going to pull out the functionality that's kind of hard, figuring out what to actually do once we found the node we need to delete. This is a good practice just because it keeps your methods from getting too long, and you can figure out based on when things do go wrong, which part of the code actually has the problem. Did things break because you couldn't find where you were going? Maybe this is the part that has the error. Or did things break because you deleted the wrong thing? Probably this function has the mistake. So we're going to need to make delete root do something. And one thing we might try to do is set self.root to be none. This is okay. I mean, it would remove the old value of the root, but this only works if the tree is just a root and has no children. So if you remove it, then the tree is empty. But importantly, we also need to make sure we set left and right to be none as well to make sure we keep our representation invariant. Remember what we said before, the only time you can have none show up is if the whole thing is empty. So if we've found a root that we need to delete, and the left side is empty and the right side is empty, then that means we found a leaf and we should just be erasing it, having an empty tree left. Now, what happens when the tree has at least something else? You can't just set self.root to be none because if the root value is none, then you suddenly would have a child that isn't, and that's violating our representation invariant. So you can think of it as like a hole in the tree that you've drilled in because you only removed the root and didn't take care of the stuff underneath. You could analyze the tree structure to detect two easy special cases. One, when one of the trees is empty, but the other one isn't. In this case, it's pretty simple. You promote the other subtree up. So if the left side is empty, but the right side isn't, then whatever the, and so this code here looks a little lengthy, but here's the short of it. Whatever the root is of the right subtree, you just move it so it goes up one level. That's the new root, and you leave its children where it is, and that should be okay. And similarly, the same thing goes for the other side. If the right subtree is empty, then we're promoting the left subtree. Grab whatever the root is of that subtree, move it upward. It's now in the place of the node that you deleted. Now, lastly, we need to handle the case where both subtrees are non-empty. So rather than restructure the whole tree, because it's going to take forever, we fill the hole by replacing the root with another value from the tree, and then removing that other value from where it is. So if you have to think about this for a moment, which you should, there's only two values that you could replace it with and maintain the binary search tree property. Option one, the biggest number from the left subtree. And remember, the left subtree is supposed to be all the smaller things, so whatever is the biggest one there is the only one that can go up to the top. Alternatively, you can use the smallest value in the right subtree. For our code, let's go with the left subtree here. So if there are, if the subtrees are both non-empty, all this other code is from the same from before, we're going to call extract max from the left subtree. And extract max is going to find, remove, and return the maximum item on the left side with the precondition that the tree is non-empty. So our helper is going to need another helper, but you know what? That's fine. And finding the maximum item in a subtree is actually pretty easy. You just go right, because the right side is always going to be bigger. So you keep going right until you can't go right anymore. And that's the biggest thing in your subtree. removing that maximum is much easier than our original problem of BST deletion because that maximum has at most one child on the left. How do you know that? Think about it for a minute, and the answer should hopefully be obvious. If it had a second child, that child would be on the right, and that would be bigger, and you should have kept going. It means you didn't go far enough. So here's the method. We're trying to grab the biggest item from our left subtree. So we look at the root there. Is the right empty? If it is, we have finally reached the largest element of our subtree. So that's the maximum item that we have. That should be our new root, the one that we're going to move up. And we need to promote the left subtree. In other words, because we're taking that maximum value away, any of the children of our biggest value need to be pushed upward. So that's why we need to return we do our promotion here and then return the max item. If we haven't yet found the maximum, we need to go right one step and see if we've now found the maximum item, and we keep going until we found it. So the single base case here is actually handling two scenarios. One in which your node has a left child but no right child, as well as one where it has no children. If it's a leaf but you can't go right anymore, it's still the maximum. It also could not be a leaf and have a left child, but be the maximum. Either case doesn't really make a difference. But I recommend that you confirm for yourself that even though these two scenarios are slightly different, the code will still handle it okay. So I find generally thinking about trees, doing insertions and deletions is really, really hard without a visual component. So here is one way that you might remove a node from a tree. Now in our code, I do want to specifically mention that we look at the biggest item of the left subtree. But here's an example where we do it using the smallest node of the right subtree. So first off, let's say that we want to delete this 27. Step one, we got to figure out where 27 is in our tree. So start from the beginning. Okay, we got 32. Think about it for a second. Which way should we go? Well, you can clearly tell we're supposed to go left, but why do we know that we have to go left? Because 27 is less than 32. So we go that way. Now we compare 27 to 2. It's quite a bit bigger than 2, so we're going to go right this time. Now, we found the node we want to delete, but we need to put something in this place in order to actually do our deletion. So one algorithm, which is what we did with the code, would be to go into our left subtree and find the biggest item. In that case, that's this 21. And we take the 21, remove it from here, deleting it, and putting it over to the root. An alternative is we could go the right way. We find the smallest item of the right subtree and move that to the top. So let's do that. How do we find the smallest item of the right subtree? Well, we go right into the subtree and then keep going left till we can't anymore. So here's our 30. That's the top. Now let's keep going left till we can't. Well, fortunately, we only have to go one step, 29. So we delete our 27 and we take our 29 and put that where the 27 used to be. And boom, we're done. And most importantly, the binary search tree property is still held. 29 is less than 30, and it's bigger than everything in this left subtree.